Hello. In this video, we're going to put everything together, our motivation behind this primal dual algorithm, our relationship between vertex cover and matching, in order to outline and apply a primal dual algorithm for the vertex cover problem. And so our first step of our primal dual algorithm for vertex cover is to start essentially with a blank slate. I'm going to put all of my decision variables, my primal, in terms of my x's. If we go back to our primal, our x's here represent if we select a vertex or not. And our dual, so think here we're dealing with our primal. Skip the next one, which is matching. It just has a different right-hand side. This is our dual that we're going to deal with, and we're going to put all of our x's and all of our y's equal to 0. The first thing you should be thinking to yourself, is this feasible? And so if I put all of these y's equal to 0, well, yeah, we're less than or equal to these values and we're greater than or equal to 0. We are indeed feasible to our dual. So we start with a dual feasible solution. But when we think back to our primal, if I put 0 for all of these x's, we are not primal feasible. So we're feasible to our dual of vertex cover, but we're not feasible to our primal of vertex cover there. Okay? Once we have that, what we do is we think about our dual and we pick any edge and take the associated decision variable and raise it until a constraint becomes tight. So for example, we could take YAB and raise it as high as we possibly could, which in this case would be 1, because YAB has to be less than or equal to 1 and also less than or equal to 3, so we could raise it as much as possible until our dual constraint becomes tight. And once you should be thinking in the back of your mind, okay, what do I know once a dual constraint becomes tight? Well, my slack and surplus are 0. This constraint corresponds to a variable in my primal, and when this is tight, that variable can be raised up from 0. So we would have a constraint here that's tight, which means we can freeze all of the other edges. So let's say this is 1. All of the other edges that appear in the constraint, which is nothing here, would be 0. And once this constraint is tight, I can raise up the associated variable, which in this example would be XA. Here, and I can raise it up to 1. I then repeat, I go back to my dual and say, okay, well, I have a lot of other dual variables that I could raise up until I get, I'm going the wrong place. Here, this dual, I could have a lot of other y variables that I could raise up to make these other constraints tight. I would freeze the other variables in it, and we keep on repeating until all of these variables are frozen, and then we'll end up with the solution to the vertex cover problem. So let's go through an example on this graph here. Just so you know, this graph is exactly the same as this graph here. It just prevents me from having to swap back and forth too much there. So I also want to point out that this is not necessarily an optimal algorithm. So we are going to end up with a feasible solution for vertex cover, but it is not necessarily the minimum vertex cover. And we aren't necessarily also going to get the maximum value for the dual of the vertex cover, which is similar to matching there. So I just want to iterate that. I also want to say, depending upon what you select, you have some flexibility. So here you can pick any edge. So if you pick AB first, or BC first, or BE, or so on and so forth, any of those first, you might get a different solution than your neighbor who's executing the same exact algorithm because of this flexibility. So we're going to do one execution of it. You then have the opportunity to use this exact same graph to execute it by selecting a different set of edges to begin with. So I'm going to arbitrarily, to begin with, I'm going to select BC as my first edge. What we're going to do is we're going to raise YBC up as high as it possibly can until one of our dual constraints becomes tight. So let's look at our dual. We see YBC appears in this constraint and this constraint. Okay, well this tells me that YBC can be at most 3, and this constraint tells me that YBC can be at most 4, which means YBC here is going to be at most 3. When this here goes to 3, my BE and AB have to go to 0. So I'm going to go here, I'm going to fill these in going down, all of the values that we've just set here. Once I set this to be 3, well, this constraint is tight. This constraint corresponds to XB. So on the graph here, we've selected YBC. We've set it equal to 3, which means that all of the other ones incident to B have to be 0. So I'm going to fill these in at 0. And because this here is tight, I now have implicitly selected B to be in my vertex cover, which I'm just going to circle to indicate that it's in the vertex cover. So right now, just to clarify here, we have set YBC equal to 3, which means that YAB is equal to YBE, which is equal to 0. And then in our primal, we've set XB equal to 1. Now, let's go back, repeat, and we pick another edge. For here, again, this is arbitrary. I'm going to select CD. So in my graph here, I'm selecting CD. Okay? I then can go to my dual. I look here and I can march down CD. Okay, well with CD here and with 3 already filled in, CD can be at most 1. Here, this CD can be at most 2, and that's everything else there. So we know with this, CD can be at most 1. When CD is 1, CE has to be 0. So I'm going to plug in the rest of these that I have frozen as a result. Okay, so with this, when I have CD equal to 1, well, this constraint here now becomes tight. This constraint corresponds to C, XC. So by implicitly setting CD, or by explicitly setting CD to 1, we've now set CE to 0, what we had here. I'm just filling it in the graph. And now we've said that XC is equal to 1. Okay, let me plug these in here. So we are setting XCD equal to 1, which means that XCE has to be equal to 0, and XC is equal to 1. Okay, not all of my Y's are frozen, so I repeat. Now I'm going to select, so you have lots of flexibility here. I'm going to select DE. If I go up to my graph here, this is selecting, let me go red, DE. If I look in my formulation, I march down. Okay, well, DE here can be at most 1. DE here can be at most 2. And the reason this is at most 1, because this is frozen at 1. So with that, we're going to say that DE is equal to 1. Once DE is 1, there's nothing else that trickles through. We still have the opportunity to raise EF to 1. We don't have to force that to be 0. But we do know once we set DE equal to 1, I have this constraint here that corresponds to D, and that is tight. So let me just document this. Once I have this as tight, I can raise up XD. Okay, so we're setting DE equal to 1. Nothing else trickles through. And so with that, I select DE. I set YDE equal to 1, which means that XD is equal to 1. Lastly, the only one I have left to possibly select if I look at all of these is EF. And so I'm going to select EF on my graph here. Once I select EF, I want to say how high can EF be? Okay, well by this constraint EF can be 1. By this constraint, EF can be 4, so that means the most EF can be is 1. Nothing else trickles through, and so here we've set EF to 1. And now we look at this. This constraint here becomes tight. This constraint is not tight. My left-hand side is not equal to my right-hand side. This here, my left-hand side is equal to my right-hand side, which means that XE is raised to 1. So I'm selecting XE. Okay, so let me document this here. Lastly, we have selected EF, which means that YEF became 1 and XE also became 1. So let's plug this in and let's just see if we are optimal. Maybe, fingers crossed. So we have selected 4 values here, okay? So we can plug in XB, XC, D, and E into our objective function value. So here we have selected, let me just clarify here, we've selected B, C, D, and E. So if you plug this in, we get 7, 8, 9, 10, 11. So the objective function value of our primal is 11. Sorry, I know a lot of jumping around. So we have our primal. So let's just call it ZP is equal to 11. Let's look at the value of our dual. So here we have our values plugged in. So let's just plug them into our objective function. So this was 0, this was 3, 0, 1, 0, 1, and 1. So when I add that up, I get 3, 4, 5, 6. So the objective function value, our dual objective function value, is 6. So ZD is equal to 6. You should know here now by strong duality that we are not optimal, but we do get a feasible solution. If we think back to this graph here, in terms of the vertex cover problem, we are indeed feasible. You take every single edge and say, is one of the endpoints in the selected vertex cover, which we have circled here, and they are. So we are indeed feasible to vertex cover, but unfortunately we are not optimal. You could go through and select different arcs or edges first, and you could get a different solution, in which case it could be better than what we have seen here with vertex cover and the associated matching. So another thing you could be thinking to yourself is, hey, those red lines do not look like a matching, which you're exactly correct. They are not a matching. The problem is because of our weights here on the vertex cover. If these were indeed 1, which I invite you to try out, if these were all the weights were 1, we would get a matching, and we wouldn't get that, hey, 2 edges that are incident to C or 2 edges that are incident to D and E are selected. You would only get 1 because of the trickle through in setting certain things to be 0 there. So we'll leave it at that in terms of our primal dual algorithm. It's nice. I think you start dual feasible and you march towards a primal feasible solution. Main idea there that we demonstrated with vertex cover and matching.